recording. Okay. So in the box it says the function f has the limit L as x approaches a, and all of that is written in symbolic form. Please don't mess up with me. Right here. All right. So we would read that the limit of f of x as x approaches a equals L. All right, that's how we write a limit. And the definition says all values of the function are close to L for values of x that are sufficiently close to but not equal to a. What in the heck does all that mean? And it also says the limit L must be a unique real number. So a limit is generally a number. Sometimes it's not defined, but if it is defined, it's a limit. All right, so I'm going to just take you down to the first example and help you make some meaning of these definitions. I skipped over these one-sided limits, but we'll come back to that too. All right. So we're starting with this simple function, linear function, f of x equals 2x minus 5. And suppose we want x to get closer and closer to 3. All right, so what I have for you there is a screenshot from my calculator of values of x that are getting closer and closer to 3 from the left of 3. So I'm looking at that first table, starting with 2.5, moving up to 2.8, 2.9, 2.99, 2.999, 2.9999, and so on. So that's what we mean by x getting closer and closer to 3 from the left. All right. I don't understand. All right. And then if you look over at the y column, those are the function values in the y column. Those values appear to get closer and closer to 1. All right. So a couple ways we can say that in words. As x gets closer to 3 from the left, y gets closer to 1. Here's another way to write that. In symbols, same thing. As x approaches 3 from the left, so that little negative sign, up there, that means from the left. All right, so as x approaches 3 from the left, y approaches 1, and writing it using limit form, the limit, all right, hold on, let me just put my dogs out, hold on. Oh. Sorry, they don't understand. Okay, so what I just highlighted, we would read that the limit of f of x as x approaches 3 from the left equals 1. All right, and that's called a left-hand limit. It's also a one-sided limit because we are approaching the x value from the left. All right. The next little table, we're talking about x getting closer to 3 from the right. So the x, hold on guys, I'm so sorry. Okay, sorry, I'll put them out. They're not, hopefully they won't bother me again. And you, all right. So that second screenshot of x's starting at 3. So we're kind of backing up or starting on the right of wait a minute, something's not right there. Starting, no. Okay, that first number shouldn't be there. So cross that out. Starting at 3.2, then going to 3.1, then going to 3.01, 3.001, 3.001. That is looking at x's that are getting close to 3 from the right of 3. And again, if you look at the function values, they seem to be getting closer and closer to 1 as well. All right, so we'll say as x gets closer to 3 from the right, y gets closer to 1. We can write that in the form that I just highlighted or in the limit form as we did up above. All right, so again, that would also be a one-sided limit. That would be a right-hand limit because we're looking at x getting closer to 3 from the right. All right, and because y, and that little arrow, I guess I should have mentioned that stands for approaches or gets close to. So since y approaches 1, as x approaches 3 from both the left and the right of 3, we say that the limit of the function as x approaches 3 equals 1. So that's this guy right here, and that is called the double-sided limit. Okay. This was your left-hand limit. And this was your right-hand limit. Okay. Stop me if you have a question. Now, we can also look at that graphically. So there are always going to be several ways to look at these limits. The one I just did was looking at a table of values. All right, now I'm looking at the graph. This is the graph of that same function, f of x equals 2x minus 5. That line, that's what that looks like. All right. And we're looking at where x is 3. X is 3, but more specifically, we're not really concerned with where x equals 3. We're interested in x approaching 3, and that's really, I guess, kind of the difficult concept at first if you've never studied limits before. It's this concept of approaching a number, getting close to a number, not actually equaling the number. In this case, it's also true that when x equals 3, y equals 1. But we don't really care as far as a limit is concerned. Okay, so this is where the function is defined. When x equals 3. Okay, and it's a different concept. In this case, it happens to be the same, but that's not always true. The blue arrows that I've drawn there indicate the concept of getting close. Getting close to 3 from the left and then getting close to 3 from the right. All right. And let's say x approaching 3 from the right. And over here is where x is approaching 3 from the left. All right. All right, again, stop me if you have a question. I'll go to the next one if you don't have a question. Okay, now we're looking at, you might remember me talking about rational functions and the fact that those are typically one of the more difficult cases of everything that we do, starting right away with limits. All right, so we're looking at this function. As I mentioned, that one's called a rational function because it's a fraction. It's got a variable in the denominator. All right, and says this function is defined at what? X equals, and it's undefined at x equals 2. Why? Because 2 makes the denominator equal to 0. All right. Now, do this. All right, so this time we're going to ask you to do this along with me in your calculator. We want to put that function in our calculator. So when you go to your calculator, you want to be sure that you input the function carefully like I'm writing on the screen. All right. The numerator, x squared minus 4, should be in parentheses. And the denominator, wow, and the denominator, x minus 2, should also be in parentheses. All right, so going over to my calculator, I'm clearing out what happens to already be in there. Now I'm typing in, so x squared minus 4 in parentheses divided by, also in parentheses, x minus 2. Now, in order to use the table the way I have it set up, which is we want to be able to put in our own values for x, I need you to set up your table like this. Go to second window. Okay, the table start doesn't matter. I'll just put 0. In fact, the first 2 lines don't matter. What does matter is that you have the last 2 lines should be set up like that. Ask, the independent variable is ask, and the dependent variable is auto. So let's see if I can pop this in my, yeah, okay. So this is really important. Like I said, this is how I always set up my calculator, really for all of my classes, but in calculus is really helpful. All right. So, excuse me, again, the way I got there, you know what? Y'all didn't tell me that I didn't share my screen. So, but I guess that's okay because I just showed you a picture of it. I went to second window in order to get that, get the table set up. All right. And this is what's important, as I said. So that's putting, basically X is on ask and Y is on automatic. All right. So let me go to the calculator screen now. All right, there's my calculator screen. This is where I had input the function in for y equals. Now when I go to my table, yours is probably going to be empty because it's waiting for you to give it values of x. So the first thing I'm going to do is choose some x's that are to the left of 2. So that could be 1.5. I want to get in a little closer, so I'm going to go to 1.1. All right, what's closer than 1.1 would be 1.01. And then 1.001, and so on. You could do this as long as you want, just putting in an extra 0 in there. And if you look at the y values, hopefully you're pretty convinced that y is getting close to 3 from the left. All right, pop that screen. Okay. All right, that's what it looks like. So basically that's this table. I don't know if you can see my mouse hovering. I don't know if you can or not. But those are x's that are to the left of 2. I'm going back to the calculator and I want to clear out the table. So I'm starting at the top of the table and pressing delete. Delete, delete, delete. Clear, let me mention, suppose 5, I put 5 in there. If I press clear, it just clears the entry. So you can put in another entry. If you want to just empty out the table, like I said, you want to use delete. Right, now I'm choosing some x's to the right of 2. I'll start at 2.5, then go to 2.1. All right, now I'm going to start putting in some zeros. 2.01, 2.001. And like I said, every time I put in an additional 0 between the 2 and the 1, hopefully you can see that in each case, the y value is getting close to 4. And if you notice in the table, it looks like y equals 4. But if you highlight that, it's 4.0001. So it's not quite, it's not 4, but because of the fixed width of the column in my table, that it rounds it to 4. All right. All right, so get a picture of that, and remember to go back to our Word document.
Professor, I have a question.
Okay, I'm listening.
So I put in exactly what you did, but when I got to 2, mine says error in Y1 column instead of 4.
Oh, okay, well, I didn't put in 2. I never put in 2.
Okay.
Because you're exactly right. 2 is the number that makes the function undefined. Okay, if you see that screenshot, it looks like x is 2, but I actually put in 2.00001.
Okay.
All right. But yeah, you're exactly right, because we already said 2 is the number that makes the function undefined.
Okay. Thank you.
All right. Okay, so we say as x approaches 2 from the left of 2, y approaches 3. That's from this table. That just got bumped. As Something isn't right. Oh. Oh, okay. Okay, this table is not accurate because I got x's that were close, getting close to 1, not 2. I apologize for that. Let me fix that one up. Need x's that are getting close to 2, so I should have started. I'm just going to fix this up real quick and then I'll pop it in. Okay. Instead of that one, got rid of the wrong one. Okay, that's better. Sorry. All right, now those numbers, those are x's that are approaching 2 from the left. And so that shouldn't have been a 3. That should have been, this should be 4 right here. Okay. All right, and then write that, well, mathematically write it in limit notation. We would say the limit as x approaches 2 with a little negative symbol, means from the left, equals 4. The limit as x approaches 2 from the left equals 4. All right. And then on the other side, this is x approaching 2 from the right. Y also approaches 4. So we would write limit as x approaches 2 with a little plus symbol, means from the right, limit of the function is also 4. All right. And so because the left-hand limit is 4 and the right-hand limit is 4, so let me specify that. This is the left-hand limit. And this is the right-hand limit. Because those are the same numbers, then the double-sided limit is 4. All right, so we'll write limit as x approaches 2 of the function equals 4. This is called the double-sided limit. All right. Okay. And let me take you back to the graph for a minute. So this is actually, like I said, this is a rational function, and the graph is actually a line with a hole in it. Okay, I just do that hole to make it more visible. There's a hole in the graph, and that's because the function is undefined at x equals 2. But if we were to approach where x equals 2 from the left, we're going this way, and then approach x equals 2 from the right, the function value that we're approaching is 4 right there. Okay. All right, so stop me if you have a question on that, and we'll go to piecewise functions. So we're looking just at the different kinds of functions. Piecewise is another type of function that we look at. I believe we graphed one of these last week. So number 3 is a piecewise function with the 2 pieces there. And we're asked to find the limit of the function as x approaches 0 if it exists. So we'll see what that means. All right. Okay. B is a different question, so that's fine. All right, so looking at the graph, here we are. I'm highlighting those 2 points if you can't see because the graph is kind of squeezed in. All right, so we look at the left side of the graph. This is talking about where x approaches 0 from the left. So as x approaches 0 from the left, where is y going? Right, y is going right there. Looks like that's -3, so y is approaching -3. So we're on this piece of the graph. To talk about x approaching 0 from the right, so as x approaches 0 from the right, so now we're on this piece of the function, and we're right here, y is equal to 0. Or the y function, the y value at that point is 0. All right. So basically we're saying, okay, from the left, y approaches -3, and from the right, y approaches 0. We're not going to the same place. All right, so this is a case where the left-hand limit doesn't equal the right-hand limit. And when that doesn't happen, then the double-sided limit does not exist. Does not exist. All right. And sort of informally, we can say, oh, well, if we take our fingers, I can't show you in person, if we take our fingers and trace along both graphs heading to where x is 0, our fingers go to different places. If our fingers were to meet up, then we would be able to define the limit. That's the case up here with this graph, okay? Those red arrows. If I were to take my fingers and move toward where x is 2, from both the left and the right, our fingers would meet at the same place. So in that case, that's the limit. The limit in that case was defined to be 4. In this example, like I said, our fingers go to different places. All right. So in answering the question, we would say the limit of the function as x approaches 0. So I use the abbreviation DNE. That's DNE does not exist. All right. DNE. Question on that one? Okay, part B. Not down here. See how much I've got to go to do here. Okay. All right, for part B, we're asked to graph the function and then evaluate the limit. Oop, and that should keep getting to change that. That should be an equals. Okay, so remember we graphed a piecewise function last time. This is how you would input this in your calculator. And remember this slash, that's the division key. And the inequality symbols, these are located under the test menu, which is second math. Second math. All right. Now we're going to put this in, but it's kind of overkill, but I'll tell you why. That's actually just an ordered pair. That says, hey, if x equals 1, y equals 2. So that's just an ordered pair. But we'll go ahead and put it in. And then for y3, negative x squared plus 6 if x is greater than 1. All right. So I'm going to go to my calculator. Do you want to see me put this in the calculator? I'm assuming that you do. So I went to the calculator. All right, so I've got in parentheses 2x minus 3, close the parentheses, divided by x, and then second math, number 5 for less than 1, and close the parentheses, and press enter. All right, 2, you don't really need that in parentheses since it's just a number. 2, if x, now second math, the first item is equals, if x equals 1, and then y3 will be negative x squared plus 6, close the parentheses, divided by x, and then back to second math and grab the greater than symbol and 1. All right. So I'll put this over in, all right, so that's how I have it typed in my calculator. Actually, you can't see it, but that's okay. Now for the graph, I'm pressing my window. Okay, I'm in the standard window, which goes from -10 to 10. And let me just say, you know, a lot of you I know, so you've had experience with the calculator. If you're lacking experience with the calculator, I found a pretty good tutorial. I'll put that up on D2L if you want a little tutorial on the calculator. All right. So this is called the standard window. I can also get the graph by pressing zoom and number 6 for standard. And there is a picture of my graph. All right, that's fine. Now, notice my Y1 is blue, Y2 is red, Y3 is black. I don't see the red graph. There's a good reason for that. In order to see a particular point, you have to be in what's known as a square window. And that's, you know, it's really probably not worth going to all that trouble to show you that. But let me just show you if I press trace and go to, well, I was supposed to go to 1. If I go to where x equals 1, I said this is a lot of trouble. I have to actually be tracing along Y2. And if you notice the little cursor thing there is blinking, it's saying, hey, when x equals 1, y equals 2. But if you move away from that, it doesn't show the point. Now I know some tricks of the trade. I'm going to put this in a square window. Let me see if that still doesn't show up. So boo on that. Let me try zoom decimal. Okay, there it is. Zoom decimal. I don't know if you see that little tiny red point. But this is a window that is called a friendly window. Just means that the pixels are have the same ratio, and so I can actually see that point. Not a big deal, but I can't see everything I need to see, so I'm going back to zoom standard. All right, because in reality, it doesn't really matter that I can't see that point. All right, so I'm heading back over to my document. You should see my Word document now. And let's see. Ooh, there's a little point right there that I wanted to be in red. All right, so here's what's going on. They're actually open circles at the, whatever you want to call those, the kind of the blunt ends of those graphs. And that's because for a function, there can only be one place where x equals 1. And that's at that closed circle that I drew right there, okay? So this little point, this is where x equals 1. But it turns out for the limit, we're interested in the limit as x approaches 1. We don't really care about that point, because here's what we do care about. We want to get close to 1 from the left. I'm going to be on the blue graph. As x gets close to 1 from the left, I'm tracing along this graph. I'm heading to the y coordinate of that point, which I think is -1. So at this open circle, y equals -1. And that's going to be my limit. At this open circle, y equals 5. And there's actually another way I can tell that. Let me get rid of this graph. Oh, actually. Now kind of mess things up. Okay. All right. So what am I doing here? What I'm trying to do is evaluate the limit. Go back to the problem. I want the limit of the function as x approaches 1. So now I hope we're ready to answer the question. Looking at the blue piece of the graph, we'll say as x approaches 1 from the left, y approaches -1, and as x approaches 1 from the right, y approaches 5. Basically, because those aren't the same numbers. All right, so I'll say since -1 and 5 aren't the same, we'll say the limit as x approaches 1 does not exist. And a little more formally, we'll say lim as x approaches 1 for my function d in e. All right. Let me just stop and make a general comment. This is kind of what, I call it theoretical mathematics, limits. And you may be wondering, if this class is geared towards applications, why are we studying this? Well, the reason is the definition of a limit, or the concept of a limit, is actually involved with the definitions of several things that we study, one being the derivative. So, and the derivative is what we spend most of our time on. That's why we start off talking about limits. It's perhaps not the easiest thing that we talk about because it's kind of abstract, but I always say, just bear with me. This isn't how the whole course is going to be, I promise. Okay. All right, let's see. I may want to change. I'm going to change gears. And I'm going to come back to limits at infinity rather than give you all this. That's pretty abstract too, thinking about infinity. So I'm going to hop over to section 1.2 and pick up some stuff there. It will open my document. Oh no, don't do that. Okay, looks like maybe go to the PDF version. Not recognizing. Oh, not recognizing my equations. Brr, always something. All right, so if I can find it. All right, so you should see section 1.2, algebraic limits and continuity. So you probably feel a little bit better about some of this stuff because here I can give you rules for finding limits. All right. All right, this says we'll consider limits of polynomial functions and rational functions, and also piecewise functions. So we start with the easiest cases, the polynomial. Actually, the easiest case is a constant function. A constant function is simply f of x equals a constant. Okay, a number. F of x equals a constant is just a number. So that's the first and easiest case. The limit of a constant function is that constant, no matter what value of x we're looking at, no matter what value of x. So for example, 1a, here's my constant function, -3. The limit of a constant is a constant, so that limit is -3. The x value doesn't matter, be anything. All right. For a polynomial function, that's going to be real straightforward. Find the limit of a polynomial function at a value c. We just substitute c in the function, plug and chug. So for part B, we want the limit as x approaches -2. We simply substitute -2 in the function. -4 times -2 is 8. And so again, right away, you see that that's the simplest case, polynomial function. All right, well, the next one, that's still polynomial function. So plug in 2. Just be careful. 2 squared plus 1 times 2 squared minus 4. 2 squared is 4. 4 plus 1 is 5. Again, 2 squared is 4. 4 minus 4 is 0. 5 times 0 is 0. Okay. For part D, the limit as x approaches 1, I'm sorry, -1, so we plug in -1. That's -1 cubed minus 2 times -1. So -1 cubed is -1. -2 times -1 is +2. -1 plus 2 is 1. All right. That's pretty straightforward. Now, I always like to tie all these in together. We just talked some about limits of graphs. So I have the graph of the function that we just did in part D. Here it is, x cubed minus 2x. We were interested in the limit as x approaches -1. That's right here. All right, so from the left and the right of -1, looks like I'm heading to where I just put that x, and the y value is 1. So graphically, it's also true that the limit of this function as x approaches -1 equals 1. All right. Now we come to the not so easy case. rational functions. So, I mean, you can look at that. There's all these rules for rational functions finding limits, and that's because of that denominator and the possibility of getting 0 in the denominator. So there are 4 things that we pay attention to, and it's basically looking at where zeros can occur. So to begin with, it says to begin with, we just substitute C. Stop doing that. Okay. To find the limit at a value C, we just substitute C in the function. All right. One of 4 things will happen. First of all, you'll get a fraction with no zeros. No 0 in the numerator, no 0 in the denominator. That's the limit. An example of that would be 2a. All right. So to begin, I'll just go ahead and substitute 2 and see what happens. 2 squared minus 3 divided by 2 plus 4. Well, that's 4 minus 3 is 1. 2 plus 4 is 6. 1 divided by 6 is a perfectly good number, so that's my limit. All right. Let's just hop over to the next one. We'll go ahead and substitute 4 and see what happens. So 4 squared minus 4 times 4 divided by 4 minus 2. Well, that's 16 minus 16 divided by 2. That's 0 divided by 2. And 0 divided by 2 is equal to 0. If you don't believe it, put it in your calculator. So that's the second case. 0 divided by a non-zero number equals 0. 0 divided by anything except 0 itself. And so the limit in that case equals 0. The problem comes as before when you get a 0 in the denominator. So I think probably that's going to happen in the next couple of cases. So I'll just go ahead and start with part C. Begin by substituting 1. That's 1 squared plus 3 times 1 plus 2 divided by 1 minus 1. That's 1 plus 3 plus 2 divided by 0. That's 6 divided by 0. All right. 6 divided by 0 is undefined. There's nothing new there. I mean, and so the limit does not exist. I'll write out does not exist. But this is the case where we had a non-zero number divided by 0. That is just flat out undefined, nothing else to do with it. The limit does not exist. In the case where you get both a 0 both in the numerator and the denominator, and that's up here, this is going to be something that you may not have ever heard of before. The expression 0 divided by 0 is a special case. It's said to be, it's up there bolded, it's indeterminate, which means cannot be determined. That's different from does not exist, okay? If something doesn't exist, it doesn't exist. If something is indeterminate, that means we don't know it exists, but we don't know what it is. All right, different concept. So when this happens, and you'll know it happens because you'll get 0 over 0. So if we just go ahead and substitute like we had before, we get 0 divided by 0. All right, that doesn't mean undefined. It's that new concept, indeterminate, which just means right now we can't tell what it is, but it does mean that the limit exists. The limit does exist. So how do we find it? We got to do a little work. And if you go back and look at what it says the limit cannot be evaluated until the numerator and denominator of the original function are factored and the function is reduced. Then you substitute again, and that's how you get your limit. All right. So I wish I could change colors on my PDF, but I can't. All right, so you got to go back. You're basically going to start over. All right, what am I doing? Ooh, I did not mean to do all that stuff. Oh, I did all that stuff. Start over, factor. Now, factoring may not be your greatest skill. If it's not, then you could also work this, solve this graphically. But notice x squared minus 4, that's in the factoring world, that's what we call a difference of two squares. It factors as x plus 2 times x minus 2. And then I can divide out the x minus 2. So my original function is reduced to x plus 2. All right, so I started over, I factored, I simplified or reduced my fraction, and now I substitute again to get the limit. All right, so I substitute 2 for x, 2 plus 2 is 4. All right. So like I said, that's, that's what happens with these rational functions. The placement of 0. And I think I have a graph of that one. 4. Oh, sorry, we haven't done 4e. What's my time frame? Boy. All right, excuse me. All right, let's do part E. And I'll kind of stop and see where we are. Now, some people say, hey, what if I just go ahead and try to factor that first and save some time? You can certainly do that. If you think it'll factor, go ahead and try to factor it. But let's go ahead and start by substituting the 1. The 1 squared minus 3 times 1 plus 2 over 1 squared minus 1. So that's 1. That's another 0 divided by 0. All right. And again, this is indeterminate. The limit exists. Basically start over, factor. Factor and reduce. All right. So, and let me just say, you guys are resourceful, probably, in the world of the internet. There are lots of things, lots of places you can go that will factor stuff. So if you need help factoring, find some kind of help, online help that will do some factoring. There are programs out there. I don't know their names, but it's okay with me if you do that. All right. Okay, so I've factored. The top of that fraction is a trinomial. I've factored it as x minus 2 times x minus 1. The denominator is a difference of two squares. I factored x plus 1 times x minus 1. The x minus 1 divides out. The function reduces to x minus 2. I don't know, is this thing doing weird stuff for me? X minus 2 over x plus 1. I substitute again. I feel like this is about to shut down on me. All right, so I take the 1 minus 2 over 1 plus 1 is negative 1 over 2, and that's my limit. Okay. So is there any question on that one? Kind of got bombarded with limits today. Like I said, I promise once we get through the next few sections on limits, it won't be like this. All right, this is just how we start, because how all of calculus is based really on limits. All righty. Question, anybody?
No, ma'am.
Okay. All right. All right, well, I'll go ahead and stop recording.